Alright, so here we have a relative motion problem. And relative motion is one of the trickier segments of 1D kinematics. It's definitely one of the toughest to deal with conceptually. So the key to relative motion is that you've kind of got two separate things happening, and somehow you want them, some part of them to be the same. Okay, so in this case we've got a biker starting at rest and trying to catch up to this runner. We know the biker starts at rest at an acceleration of 1.5 meters per second squared, and we know the runner has a constant velocity of 7 meters per squared, or 7 meters per second. We know the runner has a 60-meter head start. The question is, how far will the biker have gone when he catches up to the runner? Okay? So, we want to separate these two things. Okay, so we've got a biker here. A equals 1.5. Again, we're taking to the right being positive here, so everything should be positive. V initial equals 0. Don't know V final, don't know change in x, don't know t. Or at least we don't know yet. How about for the runner? For the runner we got A equals 0, V initial equals 7, which means that V final is also going to equal 7. And again, we don't know t. We don't know change in x or t. Okay? Now, the question is, what has to be the same for the two of these guys? And the answer is two things. Time has to be the same, okay? Because we're both starting at the same time. All right, guy running and guy biking are going at the same time, okay? And change in x's aren't going to be exactly the same. They're going to be close. So let me label this. Change in x biker, change in x runner. And what's going to be the same about them? Well, change in x biker is going to equal 60 plus change in x runner. And the reason is because however far the runner goes, he already had 60 extra meters. Okay? So now we can start plugging stuff in here. Okay, we got don't know time. We do know change in x. For the biker is going to be the initial times time plus 1/2 at squared. Same thing for the runner. The initial times time plus 1/2 at squared. All right. We then plug those into this equation. Okay? And so we get the initial, which is 0, so 0 times time plus 1/2 times 1.5 times t squared equals 60 plus 7 times t plus 0, 1/2 times 0 times t squared. Now, it's really important that we know time is the same for both of these, for both the biker and the runner. Otherwise, we can't solve that equation because they're different times. But we do know they're the same, so we can solve it. And it should reduce to 0.75 t squared equals 60 plus 0.7 t. Oops, sorry, not 0.7, just 7t. Okay, we rearrange, we get 0.75 t squared minus 7t minus 60 equals 0. At this point, you'd want to use the quadratic formula, which I won't throw it out there for you, and we should get that time is equal to 14.76 seconds. So that both times are 14.76 seconds. 14.76 seconds. Now the question is, which of them, what are we actually looking for? And the answer is the biker's change in x. Okay? So we're basically done with the runner at this point. We're just looking for the biker. And so we want to plug back in here, and so we get change in x. The biker is still equal to this, which is 1/2 times 1.5 times 14.76 squared. And we end up getting 163 meters. Okay? Again, a lot of that just looks like 1D kinematics. So the key component is figuring out what we can assume the same is and what's like similar but not exactly the same. The biker and the runner didn't go exactly the same distance, but there was a way to relate them. They did have exactly the same time.